on bounded storage key agreement and one-way functions by Chris Druska. And Chris is here. And soon the slides will be as well.
All right, good. So let's start with one-way functions. So most of our computational primitives, they imply one-way functions. One-way functions imply that NP is not equal to P, so that's kind of the main reason why usually we need assumptions in cryptography. And so a very natural question has been asked, which is, and this even holds in the fine-grained security setting, somehow we seem to require assumptions when we look at the time of the adversary. And so a natural question that has been asked, what if we bound the space rather than the time of the adversary? How does the landscape look then? And so actually in that setting, we can get key agreement with unconditional security, although there is a little star. So we can get fine-grained security. And so let's look at how this nice fine-grained key agreement protocol looks. It's a protocol by Prashant and Maurer, and it achieves quadratic space gaps. So the idea is essentially a collision bound. So Alice sends a bunch of random symbols to Bob, and then Alice stores a bunch of these random symbols, and Bob also stores a bunch of these random symbols, and then afterwards they exchange which symbols they stored, and then they extract a key from the random symbols that were at the positions that they both stored. And so kind of if you set your constants right, then Alice and Bob will have a bunch of them, but the adversary, if the adversary has less than quadratic space, then the adversary will not kind of store all of them. And of course, you have to consider more general attacks, but just as an intuition why this quadratic gap is kind of nice and natural and follows from collision bounds. One maybe small caveat of this protocol, which will apply to all protocols that we consider in this talk, is that the honest communication needs to be larger than the storage of the adversary. So if you actually want to consider running this protocol in a world where there are no one-way function, you would really need some extremely super high bandwidth specific infrastructure. And you can discuss whether that's feasible or not, but I want to put it out there because, yeah. Okay, so now we have this super nice protocol with this quadratic space gap. So question is, can we be better than a quadratic space gap? And unfortunately, the answer is no. And to show that we cannot be better, we need to come up with a generic attack against any protocol that runs in quadratic space. So how does this generic attack work? Is brilliantly simple and very nice. So the attacker, while Alice is sending her stream to Bob, the attacker just runs Bob S times in parallel and stores all these states. And so, okay, so for this protocol, it's kind of plausible that this works. You store S-square positions. If we send here S-square symbols, we roughly spare essentially most of the symbols, so that makes sense. But now in general, so what is the general class of protocols that I look at here? For now, I want to look at the two-message protocol. Alice sends a long stream to Bob, and then Bob sends back a short message to Alice. And so, okay, so why does this work? And to do this, to show that this works, I want to look at a very nice statistical distance version of the analysis of Dembowski and Maurer. It's by Doris Quach and Wicks from last year, and it's a really, really nice lemma that we'll use in the proof. So it goes as follows. The statistical distance between the state of Alice and the state of Bob, and these bunch of Bob states, is very close to the same distribution, but where we replace the real Bob with a Bob that is sampled conditioned on the Bob states. Here's this quickly say what the bound is and why this bound makes sense. So if Alice has space S, then the entropy of her state is S mod S. If we have constant times S many Bob states, then we have 1 over a constant, and square root of 1 over a constant is kind of small-ish if your constant is large enough. So that's kind of why the statistical bound is small. And if you want to prove this, you can use the chain rule for mutual information and Finska inequality, but I don't want to go there now. But okay, so why is this useful? This is useful because Alice and the conditional Bob, they don't have any secrets from the adversary. And so essentially the adversary can just sample from the proper distribution of the conditional Bob, and except for correctness error, it gets the same key. So we roughly get the following bound to distinguish the real key from a random key. We lose the statistical distance from the previous slide and the correctness error, roughly. Okay, so now we have a very nice construction, secure up to S square space. We have a generic attack that takes S square space. But now let's say that we are in a world where we want to get a little bit better bounds. Can we somehow go beyond this information theoretic setting? Let's say we're in a world where we don't have public key encryption, but we have one-way functions. What can we do? Can we get something better? So we want to bind not only the space, but also the time of the adversary and assume one-way functions. So actually we can do something very simple. Let's go back to the protocol that we had, where Alice sends a bunch of random symbols. Instead of sending random symbols, Alice can send pseudo-random symbols, and instead of storing as positions, she can store the PRF key. She doesn't send her positions to Bob. Instead, Bob just sends all of his positions to Alice, and then they extract from the random symbols at all of these positions. And now Alice can recompute the pseudo-random values because he has a PRF key. So now we can get arbitrary Pauli space gap. Why? Because we can choose this polynomial of symbols that we send to be large, an adversary, I don't know, C over a constant, and then the probability that the adversary stored all of the symbols intuitively is small. So then we get any Pauli space gap assuming one-way functions. So in the paper, we had a discussion that was very optimistic about extending this to everlasting security. That does not work. Still need to include this into the ePrint version, but just wanted to put that out here. Okay. So, now we have very nice construction with an arbitrary polynomial gap. And we assume one-way functions. But is this necessary? Do we actually need to assume one-way functions? Maybe, I don't know, maybe some other assumptions, NP not equal to P is enough for BPP. So let's look at it. Let's say we have a protocol that's secure against a little bit more than S square state. Actually here a constant would be enough. Do we get one-way functions? Let's see. So let's go back to our distributions. So we have these two distributions. And we know from earlier that these two distributions are far from each other. But also, if this is a protocol that's secure against S square space, then these two distributions are also indistinguishable. So we have two distributions that are computationally close but statistically far. And Impagliazzo and Luby say this gives us a distributional one-way function. So what is this function and what is a distributional one-way function? Firstly, this function, you don't need to read all of this. This is essentially enough randomness to sample all that needs to be sampled. And if the bit is 0, the function outputs the left distribution. If the bit is 1, the function outputs the right distribution. And so it's hard to find uniform pre-images for this function if this is a secure key-agreement. Why? If we can find uniform pre-images of F, then we can determine the bit B, and then we can distinguish real from random keys, and thus break key agreement. Okay, so this is a maybe not a one-way function, but it's a distributional one-way function. And maybe it's not even a distributional one-way function, it's a distributional one-way function that's secure against space-bounded adversaries. But now if we want to think about space-bounded adversaries, let's think one more. I mean, that this function is hard to invert for space-bounded adversaries is pretty obvious, because, I mean, we don't have any limit of the randomness that the parties can use, so the adversary can't even write that randomness. I mean, you could consider some model streaming adversary or whatnot, but let's say that we really want that the input is short enough so the adversary can write it. Okay, I mean, let's de-randomize, that's what we would do. But, unfortunately, how do we de-randomize? Yeah, we want to show that one-way functions exist, so we can't assume cryptographic PRGs. So therefore, we have very, very nice complexity theoretic PRGs for space-bounded computation. So Nizan gives us a PRG for functions with a single bit output, and with a slight adaptation of the proof, this also suffices to de-randomize multi-output bit functions. And then, indeed, this function is a function that's hard to invert uniformly for space-bounded PPT adversaries. Okay, but now you might wonder, okay, for the protocol we built, we started from a PRF, so can we do all the mini-crypt reductions and go from a hard-to-invert uniform distributional one-way function to a PRF? We kind of can, and with some loss in the bounds on each time. And also, kind of for the last PRF, we need to be careful because the truth table of a PRF grows with the number of the adversary's queries and the adversary time. So we instead need to look at a slightly weaker notion, which is a sequential PRF, which is queried on 1, 2, 3. Then the game doesn't need to store the whole table, and the reduction becomes low space. And yeah, this is a very nice reduction for the GGM construction and suffices for applications. So from there, we can go back to key agreement, and from there to distributional one-way functions. But these reductions are highly non-tight. So it's not an actual equivalence if you look at all the parameters. Okay, so in addition to our construction, we have this implication that if we have a secure key agreement that's secure against more than quadratic space and PPT adversaries, then we get space-bound distribution PRFs, and from space-bounded distribution PRFs, we get space-bounded sequential PRFs with highly non-tight parameters. And then we have a further result for the multi-round setting and the fully streaming setting. And I just want to give you a really, really brief look at the multi-round setting. So, okay, what happens if we add more messages? So, a bunch of more messages. So, Doris, Quach, and Wicks showed that the situation is much better than in the quadratic gap setting. So, more rounds, better bounds, but also, at some point, if your adversary has too much space, then it's not information theoretically secure. And their main technique is a very cool round reduction argument, which uses the trick that we discussed in the very beginning. So we replace the first message from Alice to Bob by a bunch of Bob states that Bob samples himself and sends to Alice. And this way, and then Alice does reverse sampling of her state condition on these Bob states. Highly inefficient, but works in the information theoretic setting, except that for us, we somehow need to do this reverse sampling efficiently. But how do we do this? Can we do this? Maybe we can, maybe we can't, we don't know. But if it's not possible, then it is already a distributional one-way function, this Alice algorithm. Or there is a protocol with one or less with similar correctness as security, and then we can do a similar induction argument, except that in the end we get like a large OR with one of these functions is a one-way function, and yeah, we don't know necessarily which one. All right, thank you.